So for our penny lab, what we were interested in is we rigged up these tubes, and we were curious if we were to drop pennies through this tube about 24 centimeters roughly above this whiteboard, with this center point marked directly under the tube, how far away from that center point would the pennies bounce, and at what angle with respect to this zero line? So if we were to drop pennies, if pennies fell here, here, and here, we'd be interested in this distance and this angle. For example, and we would record that for all of the pennies, and we were curious what those distributions would look like.
Right, so the first step in our procedure is to build an apparatus similar to this one that will allow you to drop a penny straight down from a specified height above the ground, in our case around 24 centimeters. So you drop a penny edge down through the tube here. You see where it lands, and you mark that point off, and then we repeat that 10 times per person. Alright, so once each person has done their 10 drops of the penny, you want to measure out a distance and an angle here. So we're looking for the radial distance and the angle from the zero line. So the radial distance, that's this dotted line here, measuring from the center dot to, and each of your penny drop, or like each of the points the penny stopped at. So you read that out, and then for the angle here, we want to use the distance here and here. Using trigonometric identities, can calculate that angle and then read that out as well.
At 2.5 centimeters. And 3.3 radians.
When we inspected our landing angle data, we found that it was too random to fit to any distribution. This makes sense, because we didn't control for any variables that happened as the pennies were landing. Now, when we inspected our radial distance data and tried to fit it to distributions, especially the normal distribution, we found that it was skewed. So, we decided to try out a log normal distribution.
Unfortunately, when we fit our data into a log normal distribution, we saw that the data was skewed the other direction. And so because of this, we decided to not go with the log normal fit and instead stick with the normal distribution, because we thought it fit our data better than the log normal one did.
Alright, so as a group, we do believe a normal distribution is justified. A normal distribution typically has the following characteristics. It's symmetric about the point x equal to mu, which is at the same time the mode and the median, and the mean typically divides the data in half. So as you can see with our graph and our histogram, this matches our data, as our mean is 21.2 and our median is around 20.5. And our graph is symmetric about the point x is equal to mu, and which is perfect. And lastly, our mode is 2.5, but this is fine even though it doesn't match our data, as our data was continuous. So if we actually make our data discrete and fit it to bins, we do see that majority of the data falls within the bin 20 to 25, which is around the same as our mean and the median. So it basically matches the characteristic I laid out at the start. And also, if you just think about this logically, it does make sense that our data fits a bell curve, which is typical of a normal distribution, as the coins would typically not fall close to the central radial point, and it wouldn't fall far away from the radial point. It will fall in a sweet spot, which is what we saw.